Let's draw back and review just for right here. So these are the ones we're going to talk about, right? Okay, starting off with bimetallic strips. Then we looked at the different temperature measurements: Celsius, Fahrenheit, absolute zero, Kelvin, and Rankine. And this is where we got to. So what we did is we had the physics class that I used, we had a chamber that we put a piece of metal, and they were metal rods. We used to have them around here when I taught physics, or when I had physics. And then what we would do is over here we had a dial indicator that was measuring the tip of that metal. And then what we did is we put steam into the thing. And guess what happened? It expands. And then we went to brass, and I think we had aluminum, we had steel, I think we had copper. But we went through different metals, and we noticed that every metal had a different expansion ratio, which they refer to as the coefficient of expansion. So what they've done is they've taken two metals that have different coefficients of expansion, and they've literally bonded them together. And this is why it's called a bimetallic strip. So they're bonded together. And what happens is when we heat these things up, the one that expands fastest compared to the one that expands the slowest is going to cause this thing to warp. And of course, how much it warped would be proportional to the heat that this, or the cold. So if I cool it down, it would warp the other way, right? You understand? And if I cool it up, it would, yeah, it just curves. Or it comes out of a spring. Let's see if we see that used a lot. You okay? Okay. So this is showing you this. Two metals bonded together with different coefficients of expansion. And when we heat these things up, what do they do? They warp. We take that warp and we can actually do a little math, and we could actually calculate the temperature by how much it warps, right? Does that make sense? So they take these bimetallic strips and they put it in all types of positions. Okay. So this is helical, which means helix, which is this is probably more, this would just be a frame. This is helix means it's in a screw, like a screw type situation. So what would happen here is that when we heated this thing up, depending on which metal was on the outside, it would either, this guy right here would either swing to the left or swing to the right.
So it unravel?
Yeah, it's either going to get tighter or it's going to unravel, depending on which metal's on the outside, right? Of course, this is just going to do what? It's just going to come out of it's either going to try to get tighter in the spring, or it's going to try to come out of the spring. Now, we like that one because originally when they came out with heaters, they came up instead of constantly controlling the temperature of the heater, what they decided to do, and these are still used in basically these old floor heaters that you buy that regulates the temperature. But this is actually a real thermostat that came off an old, had one of these in our house, guys. This was working. Might have to pass it around, but I sure need to show it. I know what I can do. The whole front's been taken off. But this is the way you would set the temperature. Here's the bimetallic strip right here, and it's in a coil. And then at the top, it's got a mercury switch. And so what would happen is I would set my temperature, and I'm either going to make the coil tighter or I'm going to loosen the coil up. with this right here. And then of course when it heats, what would happen, this thing would come up here and start tilting. And then depending on which direction it is, I don't know if you can see it, but there's a contact up here at the end. I'm going to pass this around. Don't drop it because it's mercury, right? If you broke it, you're going to have to pick it up, right? So there's a contact up here, and there's a contact back here. So depending on which way the spring ran, if it went this way, then of course it would cover up the contacts on the back, or if it went this way, it would cover up the contacts on the front, which is pretty neat. And you'll probably still run into these on houses that's been around for a long time. Most thermostats now use a digital thermostat, you know. It uses an electronic sensor to sense the heat instead of using a bimetallic strip. But be careful, this is mercury, right? You know, mercury is very dangerous. What is mercury? Well, mercury is a metal, but the melting temperature is like well down below that. So we know mercury as a liquid, but it's just a metal that's above its melting temperature. So that's why it looks like a liquid. We got some here.
What's the contact demonstrate?
Yeah, this is, you can see the little contact on the front. See the little thing sticking out there and in the back. So this is basically what we have here. So when the string goes up, it either wraps over, causes the mercury switch to tilt one way or tilt the other. And it's got a little calibration on it. I didn't show y'all that, where you could actually calibrate or set it for the right temperature. These guys are pretty accurate. Bimetallic strip contacts, we use these a lot in things that when it gets hot, we want to cut them off. So what we'll do is we'll put the current through the metals. All metals have resistance, right? You understand? And what happens when you put current through resistance? Yeah, we're not looking for that. Voltage is not heat. It's called I square R. P is equal to I square R. So anytime you put current through resistance, you get heat. Right? You understand? And of course, that would cause this thing to make or break depending on heat. These are all, hair dryers use a lot of these. They'll look like a little torpedo in there. So if your hair dryer gets too hot or pulls too much current, what'll happen is people won't clean out the thing on the back and they'll start getting clogged up. And then the motor starts bogging down and starts pulling more current. And then it'll kick out that little thermal strip in there. A lot of motors have this in here. These are very, very dangerous because what they do is if you overload the motor, it'll kick it out. But what happens when these things cool down? They start back up. So you got to be real careful if you do it. So just about all the motors that are used inside an HVAC system use these little thermal heat overloads inside the motor. Very, very popular. Basic operation of circuit breakers. A lot of circuit breakers use bimetallic strips. Except what they've got is they've got a latching mechanism. So if it pops, it latches in the open position. Right? You understand? So even if the bimetallic strip closed down, it's latched in the disconnect position. And what do you have to do on a circuit breaker? We call it popping, but when it senses an overcurrent, you have to reset it, right? You understand? And then bring it back. Because if you didn't do that, if it didn't have that latching mechanism that latched it when it was open, that sucker, as soon as it cooled down, it would do what? It would come right back in there. Oops. Very popular. So this is the bimetallic strip. So here's the bimetallic strip right here. And then of course all the current comes in, goes to the bimetallic strip, and then goes back through the closed contact, which is this contact right here. And if it heats up, what does it cause to do? All this thing is sitting there on a cradle that's ready to snap. And then once it snaps, then what do you have to do with it? You have to reset it. So a lot of circuit breakers are used bimetallic. Thermocouples. What they found out was pretty neat is when we bond two metals together, dissimilar metals. They can't be the same. They got to be dissimilar metals. Dissimilar metals are two metals that try to eat each other up. They just don't like each other. A good example is copper and aluminum. So if you ever try to bond copper and aluminum together, sooner or later it's just going to corrode and eat itself up. So if you ever do that, because there's still some houses, my son's house has aluminum wiring in it. So when he goes out and buys switches and stuff, he buys aluminum switches. He don't buy copper switches. You don't really have to do that. If you ever look at where Alabama Power brings their aluminum wire into your copper wire, what they do is they put this paste on there. So it's a paste that you put across there that prevents this oxidation from taking place. So what happens is when we bond these two metals together with a joint, not just bond them together, basically what they do is they melt them together. It produces a proportional millivolt EMF when the junction is heated. So the advantage of a thermocouple, it actually produces a voltage that's proportional to the temperature. Actually produces a voltage proportional to temperature. In the type of metals, and I think we've got that in this slide, the type of metals determines the temperature range. And then we have to compare it. So used to be it was done with just ice water, but now they do this electronically. So for it to mean something, and this is why we use a Wheatstone bridge, right? What do we use Wheatstone bridges for? That 4 resistor thing that we went over in class. So we can establish what zero is, right? You understand? So if I've got a resistor that's got 100 ohms worth of resistance at 0, if I came over and put a resistor and a voltage, it would put out a voltage even at 0. But what I can do is put it inside a Wheatstone bridge, right? You understand, and balance it or adjust it so when I put it in 0. So we have to do the same thing here. So normally what they do is they use what they call a hot junction. This will be the junction that is actually put into the heat. And then we have a reference junction that establishes 0. Or the ambient temperature of the unit. Thermocouple characteristics, this is pretty important to know. High temperature range does not require external excitation. Inexpensive, withstands harsh environments. Fairly fast response. Output signal is usually in the millivolts zone. Fairly accurate, requires a reference junction. And we can do what? Can y'all see what it says at the bottom? So used to, when we did labs on thermocouples, we literally got a glass of ice water and put the reference junction in ice water. So what we was doing now is we was comparing the junction to freezing, right? You understand? Which would be 0 degrees Celsius or 32 degrees Fahrenheit, depending on which scale you want. So we okay here? No. So these are thermocouples, and this is a lot of your meters. This is really used a lot in industry, because temperature is very important. Even verifying the temperature gauges that you might have available. So this meter that we have here, let's see if I can get my camera going. I'll try that. There we go. So one of the things that a lot of meters do now, a lot of meters actually provide a temperature step. And what they'll do is they'll provide a thermocouple. So here's the thermocouple right here. And this uses 2 dissimilar metals, and the metals are pretty standard. So I think we got a chart in here that basically shows you the temperature range. And this doesn't say what metals are, I can't read it. But it says this guy's good for temperatures between minus 22 degrees Fahrenheit up to 572 degrees Fahrenheit, or between minus 30 Celsius all the way to minus 300 Celsius. And here's the little thermocouple right here. So this is where they're actually bonded together there at the very end. Now, there's something very strange about this, is that if I was to come up here and take these metals and bond it with copper, then I've just created another thermocouple. So what you have to do is you have to maintain the two metals all the way back to the indicator, whatever sensing the temperature. So this guy right here has got a temperature gauge on it. So here's from a thermocouples, I think, T1, type K. We'll look and see what that means. I got to put them in here right. Oh, here we go. Sorry. Got to open them up. So right now it says it's 18.5 degrees Celsius. And let's see if I can switch it over to Fahrenheit, or 66.4 degrees Fahrenheit in here right now. And what I'm going to do is just going to come up here and touch the thermocouples. And you see it start doing what? Yeah. Well, reading the finger of my temperature of my fingers. It's not, it wouldn't actually be my temperature because these are thermocouples. So these are used a lot. In fact, out at US Steel, we look at the kind they had. They would actually use this to verify the temperature of the melted steel. So they literally had a hole in the doors on the cube ops, and they had a big old rod. They'd put a thermocouple in and they would stick it down in the steel. And of course, it would disintegrate the thermocouple, but that was just so they could verify the temperature of their other sensors, because the temperature you get the steel up to has a lot to do with what type of steel it is. You know, how strong it is, whether you're moving towards stainless steel or mild steel or whatever. That has a lot to do with the temperature you raise it up to after it's melted, and then also what you put into the steel. So they had a landing over there, had a rail on it, and them guys would come over and take big old bags of lime and stuff, and they would just throw it over the well into the steel. And they'd throw 10 bags or whatever it was to get, or they'd throw carbon in there, and it was pretty neat. It looked good. So let's back down to about where it was. So this is what they call a K, a type K thermocouple, and we'll see what that means in a second. We have a thermocouple. What's nice about this, it puts out a voltage that we can use. So if you've got a gas water heater, what opens up the main valve? Well, the main valve is opened up by a thermocouple. So you'll see a thermocouple that looks almost just like this, and it goes into your pilot light. So if your pilot light goes out, the thermocouple doesn't produce any voltage, and the main gas valve will never work. So what that thing does is it just verifies what? That the pilot light's on, right? So when they open that main gas valve, it knows it's going to light up instead of putting natural gas all into your house, which would cause things to blow up. So ice bath. So this was, like I said, when I was taking the physics class I took in college, we actually used an ice bath. So we just got a cup of water. Sorry guys. Put ice in it as our reference junction. So now we got a reference to 0, right? You understand? And now when we put our thermocouple in, the voltage that it puts out, it would be subtracted from 0, right? You understand? What's put out by 0 would be subtracted from that, and then the input I would get into my indicator would actually be a voltage that would be proportional to temperature. Here they're using a what? Here they're using a Wheatstone bridge. Yeah. Here I don't know what they're using. Oh, I'm sorry. 3 would be a thermoelectric refrigeration, and then heated oven, and then of course a lot of times we do is this guy right here. That's the most popular. So I'd almost bet this meter right here uses a electric bridge, right? So with that, we can establish what 0 is if we know what the thermocouple is. So this is what they're showing you. What they do is they basically take the hot junction, which is the probe, they subtract from that what they call the cold junction or reference junction, and V out would be equal to the voltage that's proportional to the. Are we okay? And these are just some electronic circuits that shows you how they could do it with diodes and stuff like that, which is pretty good. Here's the different categories of thermocouple. So we got a type K, which would be this guy right here, right? And this right here actually tells you what they're made of. No, it don't. Okay? So, no, it don't. I thought it did. I thought this chart that I got off the internet actually showed you the two single metals. But what these things do, now, look, a type K would actually go from 95 to 160 degrees Celsius. The meter is what's setting the limit on this thing. Okay? So here we go. This is fine. So E is a nickel chromium constantine. J is an iron constantine, iron bonded with constantine. K is nickel chromium and nickel aluminum. N is nickel nickel, yes. Copper constantine, copper nickel compensated for ethanol. I don't see chromium and alumel, that might be this right here. That's what we call it. We had thermocouples on the jet engines on the airplanes that I worked on, and it was in the combustion chamber back on the back of the jet engine. It must have had 20 of them that went in a loop all around there to make sure that the combustion chamber didn't get too hot. We had one go out, and they were I seemed like they were wired in series, so it was getting an average of all of them. So we went out there and found, and they don't like it if they don't know how hot the engines are. So that was one of the main indicators. And we went out there and found a broke wire, and we didn't know that you had to keep the same metals all over the place. So we just got a regular terminal out of our spare parts and stripped it and put it back on and clamped it back on the thing. And it still screwed up. And then when they found out what we did, they was kind of upset. But they had to fly that plane back to Lockheed, and Lockheed had to fix the call. So it was pretty interesting. So that's when I learned you have to match the metals all the way back to the indicator. So you can't change them, because if you come in and strip it off and put copper on there with aluminum, then you just created another thermocouple, right? And it's either going to add to your error, or it's going to take away. It's going to add more error into the system. So this is maintaining the metals to the instrument. That's what it says. So all these connectors and everything would have to have the what? Whatever this metal was, this would have to be the same, this would have to be the same, this would have to be the same, until it got into the instrument where it's actually measured. So on these, that's the big thing. Are we okay? And it shows you guys these things are really, really linear. So this is temperature, this is the millivolts out per degree. And anytime you see something vary in a straight line, we call that linear. Which means they're accurate, right? You understand? Now this is the one I was talking about. They call we call it chromel adenal. This is the one we had over at JD. The ones they were actually using at US Steel to stick down inside the steel. I don't know, but they had a big old long rod. They'd go up there with their space suit on. They were silver suits, and then have, because y'all don't understand how hot steel is. God gracious, it's just unbelievable. So this is just showing basically. I don't know. Here they don't show the code junction or the reference junction. What determines the resistance of a conductor? Yeah, the metal is made from, right? Or I guess type metal would be better. We do a little better job with that. What's the next thing? Yeah, well, that's way down here. Or the size. Some are not given in gauges. The gauges are used for round conductors, but we have a lot of flat conductors and stuff like that too. So it'd be the physical size. What else? Starts with a nail. So what does that mean? We're in temperature measurements. So what does that mean? We can use this to measure temperature. We can use this to measure temperature. All we got to do is get a certain type of metal. Once we do that, have a certain length. These things have to be externally sighted. We have to put, because it's resistance, right? And we're either going to use a Wheatstone bridge and put it in there so we can establish a zero, but we got to have at least a resistor in series to get a voltage out of it, right? That makes sense. So these guys right here, what type of metal from which the conductor is made, the size of the gauge of the conductor, the length of the conductor, and of course the temperature of the conductor, and we're talking about temperature. So these guys are called what? RDTs, and what does RDT stand for? Yeah. Uses a metal, either platinum or nickel or copper, increases its resistance proportional to the what? Temperature. When I say proportional, what does that mean? That means it varies in a straight line. Usually consists of a fine gauge wire wrapped around a ceramic rod. Very accurate and stable, reasonably wide temperature range, extensive, requires external excitation, small changes in resistance over its range to operate. Where do we run into these things all over the place? They're used predominantly in water heaters. If you ever worked on a water heater, it's got two temperature sensors in it, usually at the bottom and the top, and these are RDTs. This is one, I should have shown you that. This is, so this guy came out of one of the heaters. I have a, what they call a combo unit at my house. It's a gas heat, and then it's got an air conditioning in it. And of course, you really want to monitor that gas chamber, right? That float where it generates the heat. So this is one of the sensors that was actually inside the combustion chamber of my heater. And this right here is broke. Somebody broke it. This is a bimetallic strip. So what happens, there was a switch back here in the back. When this got up to a certain temperature, it would warp and cause a contact to break back here in the back. This right here is an RDT. So it's nothing but a what? A bunch of wire just loop. And then what they do is they measure, they put it in series with a resistor or with a inside a Wheatstone bridge, and they just measure its output. So the RDT comes back to these guys. So this would go to the control circuit of my heater, and then this would be the actual contact that would make or break depending on what's going on with this thermal, this bimetallic strip right here that's been up. So that unit has both an RDT in it, and it also has a bimetallic strip. So the ones that's in your water heater look very similar to this guy right here. You just have to kind of what determines resistance to that, but I don't know why I put that up there. So they usually seal it in some type of metal or something like that to keep people from knocking the thing around and scratching off the insulation and stuff like that. That was buried inside of my semiconductors, thermistors. This is kind of like a photoresistor. This guy's called a thermistor. So what do you think this guy does? Thermistor. Yeah, it varies its temperature. It varies its resistance with temperature. So these guys have to be externally excited. They're not linear. This is the problem we have. They're not linear. I think I might have a curve up here. Yeah. So this is basically a curve for a mister. Because it's semiconductors. Semiconductors have a problem with linearity. So what this is saying is this varies in a curve. So normally if you buy a thermistor or you get it, you can go on the internet and type in the part number and it will give you this chart right here. Right? The ones I saw would give you different resistances at different temperatures. If you knew the curve, then you could compensate for it mathematically. So you could bring this into the analog input of a program controller and run it through a little bit of math, pretty easy. Or you could actually set up a table and say, okay, this voltage equals to this temperature, and you could actually get a linear curve out of it. Okay. So what they do there is like your house. So these are used a lot in the thermostats used in houses. And I don't think I got my digital thermostat over here because you could actually see the things. But what temperature range do we usually run our houses in? Yeah, right around here, right? Right, in between there and probably around maybe 60. Well, if you only run it in that real small range, it's pretty well linear, ain't it? It's linear for what? Running a house. But we can compensate for this with a computer very, very, very easily. It's just that a PLC, we could bring it in, like I said. Of course, we got to convert it to volts, right? You understand that? And what's the way we normally convert to something that varies its resistance with temperature? We just put it. One way we can do is just put it in series with a watt, with a fixed resistor. So here the fixed resistors on the bottom. The one that we have up here is called an NTC, which is a negative temperature coefficient. Which means as temperature goes up, these guys, their resistance goes down. Yeah. Now, if it was a PTC, what would that mean? It means the resistance would go up when temperature goes up. But it doesn't make any difference. What we have here is that when temperature goes up, this resistance goes down. This resistance right here is the same. So if this goes down, it's going to drop less voltage, and voltage drop here is going to go down, and voltage drop across here is going to go up, right? Understand? Because it's got to be the sum of the two. Here they're applying 2 volts to it, so that means the sum of the voltage drops of these guys will always equal to 2 volts. So if the voltage drop across the thermistor goes down, then the current's going to go up, which is going to cause the second resistor to drop more voltage. So this is a very easy way to take something that's resistance goes down and make its output voltage goes up with what we're trying to do. And now if we needed to set a 0, then we would use this in a what? We'd use this in a bridge, right? And this would be my temperature. This would be my temperature right here. And then this right here would be me. And then I would have the ability to establish what 0 is using my Wheatstone bridge. So when is a Wheatstone bridge balanced? So if I came over here and this was a 5K, and this right here was a 25K. And then over here, this was a 30K. And then this right here was a 1500K. I did this right, guys. Would the bridge be balanced? Huh? Yeah, when we say balance, it means if I measure right here, if I measure right there, it's going to measure 0 volts. That's the balanced bridge. So is this balanced or not balanced? So what's the ratio of the resistors on the left? 1 to 5. What's the ratio of the resistors on the right? 1 to 5. This guy's balanced. So what you're doing is you're not looking at the size of the resistor. So 5 over 25 gives me what? 1/5. 30 over 150 gives me what? So this guy's balanced. That would be 0. So when you're looking to see if a bridge is balanced, it's not the size of the resistors, it's the ratio of the resistors, right? If the ratio of the resistors are the same, so if I came, and it's got to be in the right order. See how I did that? So if I was to come over here and swap these around, so even though the ratio is the same, so over here, if this was 150 and this was 30, then over here, this is 5 over 25. Over here, this is 150 over 30. So this is no longer balanced because just because the ratio is the same, you got to put them in the same order, right? Normally we do top over bottom. So top over bottom has to match what? Top over bottom on the other one. If it does that, then it's balanced. And what I can do, of course, is this right here could be variable. And then this right here could be a sensor that goes from, that goes from 50 to 50 ohms up to 25K. And what I could do is I could establish what a reference is, right? So if it was a temperature sensor, I would establish a reference. Now the easiest reference to establish is 0. All we have to do is just get what? Just get a glass of ice water, right? Shake it around a little bit, get it down pretty close to freezing, stick my thing in there, and I'll adjust this to measure 0. But we have to start off with a reference, right? We have to. So yeah, we're talking about thermocouples there. Not thermocouples. Thermistors are fairly accurate if you do what? If you limit their range. So this, guys, I almost guarantee you, if you've got I don't have it. I have a thermostat that I took out, the first digital thermostat I put in my house. And you can flip it over and you can see the thermistor. That's actually measuring the temperature. And of course you get these all shapes and sizes. This is the one that we have. Somebody got my alligator clips out here. I'm gonna take my thermocouple. Y'all see a thermocouple? An infrared sensor is an electronic instrument, not a standalone sensor, must be externally powered. These are non-contact sensors. Sensor detects, all it does is measure the amount of infrared light this thing is putting off. So the infrared light it puts off is directly proportional to the temperature. An object emits an infrared light that is proportional to the temperature and of the object. The accuracy depends on the what? Right. So you can get cheaper ones. I believe Harbor Freight sells one.
So you're saying you pay what you get.
Pay for you get. Yeah, this is definitely true here. So infrared is not visible to the human Nah, infrared is safe. This is what infrared is safe. Ultraviolet is bad, right? Infrared is safe. So this is why most of your objects that operate off light, like your television and your remotes and stuff like that, puts out infrared. We can't see it, but it's safe, right? Understand? It's such a low, slow wavelength. This electromagnetic wavelength between 710 nanometers to 100 micrometers. Hotter the target being measured, the shorter the wavelength. So what they're doing is they're not measuring the intensity, they're measuring the wavelength of the light. Now, no light is basically like AC, right? It's just extremely high frequency. And a wavelength would be, if we come over here and measured between like here and here, that would be what we call a wavelength. And I can give you a formula how it's calculated, but y'all probably don't. Measures effectiveness is emissivity, thank you. Effectiveness is emitting energy and thermal radiation. These are non-contact. They measure the temperature of an object that are in motion. But you got to be real careful with your aim, right? You understand? Because you're off just a little bit, then you're not wide. Now it's not going to be accurate. So that's why most of your laser guys have most of them has a laser pointer on it. So you can actually point it. Here's some images right here. So these are probably more on the line of what we can see. There's an infrared gun over there, so we have infrared sensors.
Is that what the police do right now?
So they don't use infrared sensors. The police, no, they use laser. They don't measure the temperature of your car. I mean, what would they want to know the temperature? So they'll pull you over because you're running hot, right? Understand? So they use laser, and it works basically like radar. They'll send the light pulse out. It hits your car, and then they detect how long it takes to reflect back, and that's how they measure it. Yeah. Relative to your speed. So basically, it's just like radar, but it's hard to detect, real hard to detect. I think most of them are infrared too, and I've heard things where you put rolls of aluminum foil in your hubcaps. Yeah, they did a bunch of, they went through a lot of this, yeah. Solid state temperature sensors. So an LM35, this is electronics. This guy had to be powered up. This guy is set up to measure Celsius. And linearity is 10 millivolts per degree centigrade. Accuracy 0.5 degree centigrade accuracy. Rated for full. So this thing can measure anywhere between minus 65 to 150 degrees centigrade Celsius. Suitable for remote applications, low cost use for wafer level trimming. Operates from anywhere from, this is pretty big, so you can actually operate this on a real wide range of voltages. So you can operate this off battery. Less than 60 microamps to do what it needs to do. Low self-heating, non-polarity only, so fairly linear. 1/4 degree centigrade, low impedance. So this guy right here, and we have some of these guys, but it's electronic, which means it's got to be powered up. So this is going to be, at least these guys have got to be 3-wire, right? So if an LM35 it measures Celsius, then what would an LM34 be? Yeah, it's calibrated for the Fahrenheit. So it's pretty much the same thing, but it's 10 millivolts per degree centigrade, per degree Fahrenheit. The other one was 10 millivolts per degree centigrade. I think that's about it. Oh, this is actually the little pinout that comes with the plane. I think the ones we got is in this guy right here, 492. So these would be very popular inside computers, right? Understand, measuring, make sure, these guys right here, if you looked at a lap, most desktops, the fans run all the time. These guys right here, the fans don't run all the time because why? 90% of the time they're running on battery. You want to save that battery life, so they're doing everything. So they're not going to run the fan until it needs to be run. A lot of cars do that too now. A lot of cars, when I was a kid, the fan on the radiator ran right off the engine. But not anymore. The fan now runs off a motor. Just about every car you'll see. And they vary the speed of the motor depending on how hot the car is, right? Understand? Because the hotter you can get the car, believe it or not, without burning it up, the more efficient it is. They played around with ceramics and everything for a long time, trying to make a ceramic engine so they could run it extremely hot to get really, really good efficiency. But I don't think they ever got that going. But they vary that speed, and now you can actually get out of your car, and a lot of times you can still hear the fan on the radio running. So they definitely got some type of temperature sensor. So this is just a circuit. This is with the math in here. You don't need that. And this is comparing the different scales: the Fahrenheit scale, the Rankine scale, the Kelvin scale, and the Celsius scale. Are we okay? Rankine and Kelvin are used a lot in math about doing different things. Normally we deal with these two scales right here. You just might get out there and find some type of indicator according to this. So Rankine is what scale? It's based on the Fahrenheit scale, yeah. Kelvin is based on the watt. Sounds like a good test question. So guys, that's temperature sensors. Is that all the temperature sensors out there? No. That's all that we need to talk about, right? That's all Rich knows about.